Hey, how's it going? We're going to take a look at 6.1 graph exponential growth and decay functions. So our focus is how to graph exponential growth and decay functions, applications of exponential functions. An exponential function is going to be written in the form y equals ab to the x power, where a is not equal to 0, and b, which is your base, is a positive number other than 1. If a is greater than 0 and b is greater than 1, then the function is an exponential growth. And b is called the growth factor. If a is greater than 0 and b is between 0 and 1, then function is called a exponential decay. And b is called decay factor. Now, parent function for exponential growth functions is going to be y equals b to the x, where b is greater than 1. Now, a couple things here. Your domain for this parent function is going to be all real numbers, or negative infinity to positive infinity. Your range is going to be y is greater than 0. Now, if we set up a really quick table of that function, we're going to have 0, negative 1, and 1. If I put 0 into this function, y is 1. So that ordered pair right there is 0, 1. That's where it's going to cross the y-axis. If I put a negative 1, what you get is 1 over b. Now that point's going to be right here someplace. And if I put in 1, I get b. And that point is going to be up here someplace. I say someplace because it's not an exact number, because we got to consider whatever the value of b is. So my graph is going to look something like this, where this ordered pair is 1 comma b. This ordered pair is negative 1 comma 1 over b, and again, whatever the value of b is. Your x-axis, in this case, acts as an asymptote, which means as you go to the left, as x gets smaller and smaller, the function will get ever closer to the x-axis, but in this case, it won't really hit the x-axis. So that's just an asymptote. Graph the function y equals 5 to the x power. 5 is greater than 1, therefore this is going to be a growth function. I want you all to get used to setting up a table. The points we're going to use for x are going to be negative 1, 0, and 1. So if I put negative 1 into here, I get 1/5. If I put 0 in, I get 1. And if I put 1 in, I get 5. So we're going to say that this is negative 1 comma 1/5 right here. Here's 0, 1. And up here is 1/5. So that's what my graph is going to look like. My domain is all real numbers. And again, my range, y is greater than 0. Here we have 3/5 is the value of b. Since 3/5 is less than 1, what we have is a decay. Set up a really quick table. And as I mentioned a few moments ago, let's get used to doing this. You can use the numbers negative 1, 0, and 1. If I put negative 1 into here, y is going to be 5/3. If I put 1 in, y is 1. Or excuse me, if I put 0 in, y is 1. And if I put 1 in, y is going to be 3/5. So here's -1 5/3, about right there. Here is 0, 1, and here is 1, 3/5. Now, I know it doesn't necessarily look like it, but it actually is a decay, and it's going to look like this. Again, you're going to have the same domain, which is all real numbers, same range, which is y is greater than equal to 0, or excuse me, y is greater than 0. Now, exponential models. When a quantity's increase or decreases by a fixed percent, then the amount of that quantity can be modeled with an exponential model. This, or here are your two examples. This is going to actually be a growth, and this one's going to be a decay. So I'll put a little G right here to remind you that's a growth. This one's a decay. D for decay. A is the initial amount, R is the percent increase or decrease as a decimal, 25% is 0.25, and T is time in years. In the growth model, y equals 50 times 1.29x. Identify the initial amount, the growth factor, and the percent increase. The initial amount, which is your A, is 50. R, which is the growth factor, is 0.29. And as a percent, that equals 29%. In the decay model, y equals 40 times 0.92x. Identify this, the initial amount, decay factor, and percent. So your initial amount, that's your A, which is out front, is 40. The rate, your decay factor, I should say, is going to be actually 1 minus 0.92, which is 0.08. Now that as a percent is 8%. So notice whenever this number is less than 1, you're going to have a decay. Keep in mind and remember that's going to be 1 minus 0.08. That's how I got the 0.92. Now here are a couple examples. In 1970, the population of Kern County, California was about 330,000. From 1970 to 2000, the county population grew at an average rate of 2.4%. Write an exponential model giving the population P of Kern County T years after 1970. Okay, so P equals, my initial amount was 330,000. Now remember, 0.24% is the same thing as 0.024. Okay? Now I have to add that to 1 to get my growth factor here. So my growth factor is 2.4%. And that's going to be to the T power. So that's my model. Now about how many people lived in Kern County in 1990? Okay, no problem. You're going to have 330,000 times 1.024. Now, there are 20 years from 1990 to 1970, so this T is going to be equal to 20. Now, when you put that in your calculator, you're going to get a number that's close to 530,290. That's your population. Next example. This is a real-life situation. The cost of a new Lincoln Navigator is $54,950. It's probably more like $70,000 now. The value of the car depreciates by a value of 17% each year. Write an exponential model decay given a car's value in dollars after T years. So I'm going to take 1 minus 0.17. That equals 0.83. This 0.83 represents its value currently. So you're going to have y equals, or v equals, whatever you want to put in there, $54,950 times 0.83 raised to the t power. Now it wants to know the value after 4 years. So you have 54,950 times 0.83 raised to the 4th power. Now this value is approximately $26,078.35. So lost almost 20 grand over that 4-year period. Formula for compound interest. So this is a formula you're going to use. A equals P times 1 plus R over N to the NT power. By the way, I didn't mention this earlier, but you have to know these formulas. Just put them on a flashcard and just kind of review them like you do, like, I don't know, some of your keywords in your foreign language class or something like that. Where P is your initial investment, R is the interest rate, change percent and decimal. N is going to equal the number of times compounded per year, and T is going to equal the number of times number of years invested. So again, along with the other two equations, you have to remember that equation right there. Deposit $550 in an account that pays 3.6% annual interest. Find the balance after 5 years if interest is compounded with a given frequency. So semi-annually means it's going to be compounded twice. So in this case, N equals 2. Monthly means N is going to equal 12. So here's our equation. A, which is the amount, equals 5,500 times 1 plus 3.6% is the same thing as 0.036 over 2 raised to the 2 times 5. After you put that in your calculator, you're going to get $6,574.16. Same thing, except for now N is going to be equal to 12. This is going to equal $6,582.92. Now here's the deal. The more often you compound something, the bigger the value is going to be. No, it's not a lot of money as far as these two numbers are concerned, but I want you to think about, let's say it's more like 100,000 or 200,000. It's going to be a little bit more. All right, that wraps up 6.1. Let me know if you have any questions.